Thanks, guys, for coming to Theory Lunch, and thank you to my committee for agreeing to review this talk. Today, I'll tell you about the project. Random order set cover is as easy as offline. This is joint work with Anupam, Greg, who was moved to Harvard but used to be here, and I'm Roie. And this is a work that appeared in Fox 2021, which took place in 2022. So, okay. So let's jump right in. And let me describe the set cover problem. So the set cover problem is an extremely fundamental optimization problem that shows up everywhere in countless applications. And here's what it is. So you're given as input a collection U, I'm writing this cursive U, of n elements, and a collection cursive S of m sets. In this picture, the elements are the dots. They're the labeled V1 to V6. And the sets are these ellipses. And your goal is to pick the smallest number of sets to cover all the elements. Okay, so for example, this collection of red shaded sets is a feasible solution because it covers all the elements. And of all such feasible solutions, you want the smallest one. Okay, so that's set cover. Any questions about set cover? Great. So what's online set cover? This is by now also a somewhat classic problem introduced by Alon Arbu, Hazar, Buchbinder, and Naor in 2003. And it's the same thing, only now we imagine that an adversary pre-selects the element set and it's unknown to us, okay? And instead of having the element set up front, it's going to be revealed to us one by one online. And what makes this hard is that as soon as an element shows up, so the adversary reveals one element and reveals these elements in an arbitrary order, you have to immediately commit to some set to cover this element. So you can't leave an element uncovered. Okay, so for example, V1 shows up, and when it shows up, it tells us which sets it's part of. Okay, so initially we're holding on to these empty sets, we don't know what they contain. Element shows up, it tells us it's part of such and such sets, and we immediately buy some set to cover it. Okay, so we might pick this one. An element V2 shows up, we might pick this set to cover it. An element V3 shows up, perhaps it's already covered on arrival, so there's no need to do anything. And this process continues. And what we want is that by the end of this process, that the total number of sets we select by the end of the algorithm be comparable with the optimal set cover if we had full information and infinite computing power. Okay, so this is the goal. Okay, any questions about this model?
So do you know the sets, or when an element arrives, it just says I am the part of this set?
Yeah, so you basically have these empty IDs for the sets initially, and then when an element shows up, it tells it tells us I'm part of sets 1, 3, and 5 or whatever. Yeah. Okay, so finally, what's the random order version? It's the same thing. So we imagine that an adversary pre-selects this unknown element set. Only now we force the adversary to roll some dice and then reveal the elements in a uniformly random order. So maybe it rolls the dice, and this is the order that comes out, 1, 4, 5, 6, 2, 3. And now we play online set cover, but with this uniformly random order. Okay, so 1 shows up, we play the same game. And the question that we answer in this work is, what is this random order problem? Is it more like the offline version or more like the online version? Okay, and the title of the talk gives it away, maybe in a garden path way, but we'll pretend that you're in suspense and we're wondering what the answer to this question is. Okay, so what's known about this problem? So offline, a classic result that you learn about in an approximation algorithms course is that there is a log n plus 1 approximation to set cover. Okay, for example, the greedy algorithm, which just does the following: pick the biggest set, delete any elements it covers, and then repeat until you're feasible. This is a log n plus 1 approximation, and this is the best you can do offline if you had full information. In the adversarial order online setting, it turns out you can't quite get this log, but you can get a double log. So you can get an order log n times log m competitive algorithm, where recall that m is the number of sets and n is the number of elements. Okay, so you lose an extra log over the offline best possible ratio. Let me mention one more result, which I'm calling the stochastic setting. So if you're playing the online set cover game, but you assume additionally that the elements that you're seeing are not just shown to you by an adversary, but are drawn IID from some known distribution, then you can avoid the double log and you can get log m times the support size of the distribution. Okay, now the support size could be far larger than n. N is the number of elements that you actually see in the sequence. And the support size is the elements that you could possibly see. Okay, any questions about these results? Okay, great. So there's some reason to believe that you can't do better than. Yeah, so the stochastic setting is like you're playing online set cover, the same thing. Elements are showing up online. It's just instead of an adversary showing them to you, you're drawing them IID from a distribution, and it's the support size of that distribution. So it's like the elements that could appear in this distribution. Yeah, it's not super important. It's just for kind of comparison. That's never going to show up again. So, okay, so what's known about random order? It turns out nothing as far as we know. This seems to have been somewhat overlooked, which is maybe surprising. And one reason it might have been overlooked is that there is good reason to believe you can't do better than the double log that you need for the adversarial order online setting. So that double log is tight. You can show tight instances. Yes.
In what sense is the
So assuming P not equals NP. It's a weird, like, both information theoretic and like assuming the complexity assumption. You can't do better than this. Yeah. But so often in online algorithms, the bounds are just information theoretically tight, but this one assumes some, yeah.
So could there be a lower bound that assumes nothing?
It's an open question, I think.
But there could be.
There could be, yeah. That's an interesting question. Right. Okay. So in fact, what we show is that indeed there is a randomized polytime algorithm for an even more general problem, which I'm calling random order covering IPs, which I'll talk about in the next slide very briefly, that gets a competitive ratio of order log mn, where the m and the n are inside the single log. Okay, so in particular, in the regime where m is poly n, this matches the offline bound up to constant factors. Okay, so you can view this result as a an improvement over the stochastic setting in kind of a few ways. One is that random order is kind of like drawing from an unknown distribution, okay, more or less. And so we're drawing from an unknown distribution instead of a known distribution. And the second thing is that we improve the support size term to n, which is much, much better in general. I'm not giving the stochastic algorithm enough credit. It actually has some more features that are very interesting, but sort of under this parameterization, we sort of strictly improve it. Yes.
I was just going to ask, in a stochastic model, do you need to know the distribution in order to do this with this competitive ratio?
Yeah. You really do. Yeah, exactly. It's crucial. Right. So our work is a new algorithm. It's not just a new analysis of an old algorithm. And in some sense, what we're showing is that you can learn an unknown distribution, even as you're sort of committing to a solution to this optimization problem without taking too much of a hit. Any questions?
So I think so. You're in the randomized ordering. The distribution you're assuming is not like a random permutation or like a uniformly random permutation. It can be like something else.
No, it is. But so okay, so I kind of glossed over this, but it's kind of like you're drawing like without replacement. But replacement doesn't. Like, suppose you sample the same element, and it's a no-op because it's already covered.
Oh,
so
okay,
it's
I guess my question is, what do you mean by learned distribution?
Like when you're drawing from random order, an adversary fixes the element set, and then you're seeing it in random order. So it's kind of as if you were drawing like without replacement, but the difference between without replacement with replacement is sort of nothing. But the distribution which you don't know because an adversary fixed that set system. So in that sense, it's unknown. Yeah. So I think you might have seen in my proposal, I gave a version of this talk where I presented a lower bound, where if you can wonder sort of how does this bound change with the entropy of the arrival order distribution. This is one measure of like how random it needs to be. And that's not a good parameterization because basically like there's distribution. So like a fully random arrival order is like n log n, n fact like log of n factorial entropy. And there's distributions with 1 minus epsilon and log n entropy, which lose the double log. So basically it's very sharp under this parameterization. I actually took this out of this talk because in a talk I gave, someone actually showed me a trivial proof of that fact. So it's, yeah. But in that sense, it needs to be fully random.
For example, could bounded wise independence?
It could, I have no idea. Yeah, that's a really good question. Yeah.
Let me just ask a question about the model again. So
yeah.
in the original online, just the offline. The offline problem, you just given all these sets, you just have to figure out okay.
Right.
These randomized models, like the stochastic one,
Mhm.
is that generating the set system on the fly, or is it's generating the set system itself?
Basically, yeah. So you know the sets ahead of time, and then you're drawing the elements, which are the members of the set system. They're generated on the
Notice
fly.
that ahead of time.
That's right. You just don't know what they contain. Like they're empty identifiers, and then you're filling them in with these elements
And
you're
that's
drawing.
true of the random order model too.
Exactly. Yeah.
So-
And yeah.
So let me maybe suggest the following way of saying the same thing. You have like a bipartite graph,
Yeah, absolutely.
self on the left, elements on the right. And the m elements on the left are fixed, and n elements on the right are fixed. And the edges you're going to reveal, in online fashion. So, you see first element and you reveal all its edges. And then you reveal the second element and all its edges. And so on. So is this equivalent? Right?
Absolutely equivalent. Exactly. Yeah. Did that make sense?
Yeah.
Okay. Any more questions?
It's nothing about the sets. Like when you see the sets.
Exactly.
You don't have like statistics that these two sets. You have this number of sets that have this number of items. This item you don't know its identity, but it appears in some number of sets. You don't have any.
You don't anything. It's to me was very much amazing that you can do anything in the adversarial setting.
But if you have this information, you would have
I mean, in some sense, we kind of generate something like this information from the random order model. Like, and we're matching the best possible offline thing. So there's not much more you can do unless you want to study the regime where m is exponential in n. But
I mean, couldn't it help the adversarial online to know?
oh, I see. To that setting, it could, yeah. Yeah, I'm not sure. I'm not sure. That's a good question. Yeah. Okay. Anything else? Okay. By the way, did we start around 12 or how much time do I have?
Yeah.
Okay, so just very briefly, let me just give one slide on this more general problem that we really solve. So here is a covering IP. Okay, so we have a linear objective function and constraints 1 through 5 of this form. And you want an integer vector kind of minimizing the cost function subject to these constraints. And so the random order version of this problem is the adversary. Okay, the adversary fixes this constraint set, rolls some dice, and then shows us the constraints in a random order. It should sound very similar to the set cover problem. The goal here is to maintain a feasible solution to this IP. And the constraint is that the solution be monotonically increasing. So once we increase the coordinate in order to maintain feasibility, we can never decrease it again. And so the challenge is to kind of be competitive with the optimal costs, even as you have this requirement. Yeah.
Do the vectors AI have to be non-negative?
Yes, sorry. So for covering IPs, the costs and the vectors are all non-negative. Yeah, exactly. Right, and so set cover is nothing but the special case where this constraint matrix is 0, 1. So set cover I think of as like a nice sandbox for understanding these more general IPs.
This is weighted set of top, right?
This is weighted set cover, yes, right. And in fact, we solve, yeah.
So the weighted.
Yeah, in fact, we solved this, weighted covering IP. So we solved this very general problem.
So all the results on the previous slide.
Yeah. In fact, the theorem that I showed is for the theorem is for covering IPs. So yeah, set cover is just kind of a correlate. Isaac, do you have a question?
I read one quickly.
Okay. Okay. So this is not important. I just wanted to kind of describe this briefly, but we're not going to talk about this again. Okay, so in the remainder of the talk, time permitting, I'll do the following. I'll give you some view of previous work, which is going to be kind of a history lesson. Just so because that's the first place you would probably start to look if you were trying to solve the random order version. It's very natural, and we'll see kind of why it fails. I'll tell you about our algorithm, which is called learn or cover. I'll start with an exponential time warm-up version of the problem of the algorithm, which hopefully I can explain to you in full detail. And my goal in this talk is to have you come away with the full understanding of that version. Yeah, and then if there's time, I'll tell you about how to make this poly time. There were some interesting ideas that went into this, and then in particular, like actually per David's question, like generalizing from the unit cost setting to the weighted setting required some like even further ideas. So we'll see if we get that far, and then I'll end with the conclusion and some extensions. All right. So suppose you were solving set cover. It's good to understand how you would even solve set cover. And there's a million ways to do that, but here's one that's particularly useful. It's called the method of like random rounding. Hopefully this is a review for a lot of you. But it's a two-stage algorithm, okay, for the offline set cover problem. The first thing you do is you write an LP, relaxation, linear programming relaxation, then you solve it. Okay, so what's the LP for set cover, the classic LP for set cover? You have a vector x, where every coordinate of the vector is a set, and you imagine that xs represents the fraction to which you select the set s. And you want to minimize the sum over s of xs. Okay. Now there's a constraint for every element that says, well, I want to pick at least fractionally one set to cover that element. For every v in cursive u, the sum over s containing v of xs is at least one, and everything has to be non-negative. Okay. So this is a relaxation. So the optimal cost of this program is less than the optimal integral solution. The second thing you do is if you solve this program, oops, you get a fractional vector. So that's not a legal output to set cover. So you have to round it to an integral solution. And the way to do this is to treat xs as the probability that you pick the set s. Okay, so we'll buy the set s the probability xs. Now, if you think about it, the expected cost, if I do this once, like for every set sampling probability xs, is the cost of the LP, which is less than the cost of opt. So that's fantastic. The only issue is that we might not be feasible. We might fail on some of the elements, but you can show that every element is covered with at least a constant probability. And so if you boost this, repeat this log n times, you can union bound over the elements and you're happy. Okay, so that was super quick, but basically expected cost here is order log n times opt. Okay, any questions? Okay, great. So how do we do this online? So here's how the online algorithm works. It's the same two stages, basically, just with the word online in them. Okay, so we write the same LP. And what they show, and this is kind of the cornerstone of their work, which is, has become kind of a primitive in online algorithms, is that you can maintain a solution to this LP, even as the constraints are revealed to you online. Okay, so you're learning the elements over time, and when an element arrives, it reveals one of these constraints to you. You can maintain a solution to this LP such that the fractional solution is only monotonically increasing. The coordinates never go down. And it's also no more than log m times the optimal offline solution at any stage. Now, this is very powerful because you can then round online. Okay, so in what sense can you round online? If this is your solution at time t, excuse me, and this is the solution at time t plus 1, it's increasing monotonically, so the delta is positive. And what you can do is, when x increases, you can sample every coordinate with probability only proportional to the change. And you have to kind of scale it appropriately. But what you can guarantee is that, okay, you're doing this process over time, your vector is growing, and you're sampling only according to the change as it's growing. You can ensure that the probability you take a coordinate s by the end of this entire process is exactly its LP value xs. So the convenient thing is that it's as if you're analyzing random rounding like offline with a final vector x. Okay, and we do the same thing where we boost this by log n and then union bound. Any questions about this? So none of this is going to, if you're not following this, that's okay. I'm just kind of giving you nice background, but we're actually not going to need this to understand our algorithm.
So for each element of the terms that you see, you have to solve the LP again, and then it'll increase those values.
Exactly. Exactly. So we're treating this like LP solver as a black box, but you feed it a new constraint, and it increases the solution monotonically. And
then are you rounding it continually as well?
Exactly. Exactly. Only with respect to the change, and you're kind of carefully doing this in such a way such that it's as if you just did rounding once at the end of the algorithm.
I see.
Yeah.
You're choosing some probabilistic method that just.
Exactly.
If you already selected it, you keep it.
Exactly. Yeah.
If you didn't, then maybe you select it with a little bit of probability that it's supposed to. Okay.
That's exactly right. Yeah. Yeah. So the total cost here, so it's basically like the offline algorithm. The total cost here is log n from the same rounding, but we lose an extra log m from maintaining this kind of monotonically increasing LP solution. Yeah. Okay, so just to kind of drive home how natural this algorithm is, I'm going to kind of briefly talk about how it works. So this is kind of how you maintain this log m approximate solution. So initially we have this empty set system, right? We have these sets and we don't know what they contain, and we're going to think of the LP vector as like a score for each of these sets. And initially we don't know anything, so we should initialize it to kind of the same thing to reflect our ignorance. So we'll initialize this LP vector to like 1 over m. Okay, this is to kind of get it off the ground. And then what we'll do is when an element shows up, if it's uncovered, and while it's still fractionally uncovered, we just increase the score of all the sets containing it until it's covered. Okay, and the right rate to do this at is this like exponential rate. Okay, so while it's uncovered, kind of double the weights of the sets containing it. So in a picture, kind of, if it arrives and it's in the blue and yellow sets, we'll kind of slowly double these until it's feasible. Okay, another element shows up. Now, if blue went up to 1/2, it's not feasible, so we need to kind of keep increasing that by a rate of, this exponential rate until the element in the blue set's covered, and so on and so forth. It continues. So how do you analyze this thing? This is really kind of not important, just for your well-being. It's the sort of primal dual method. So every time you double a set's LP value because of an element v, if you write the dual, there's a variable for every element in the dual, and you kind of, for accounting purposes, add 1 to this dual that caused the increase. And then you kind of do the standard primal dual analysis. You show the primal is feasible, the primal is bounded by the cost of the dual, and if you scale down the dual by log m, it's also feasible, which by weak duality means that the cost of the primal is at most log m times the optimal solution. Okay, not important, it's just if you wanted to understand quickly how this works. Okay, so basically, like, we have this algorithm, and one can wonder, does it work in random order? Does it do better in random order? So there are situations in which the independent rounding loses this log n. That's unavoidable in the analysis. You can kind of construct these examples. And one thing that we show is that well, turns out this log m that you lose from the fractional algorithm is actually tight even in random order for fractional algorithms. Okay, so you can construct situations where you can't have a monotone fractional solution to this LP that's better than log m competitive with the offline optimum. So what this means is that both stages of the analysis are tight. You can neither improve the analysis of the fractional solution, or even give a better algorithm in that sense, nor can you kind of improve the rounding. So you're kind of, it seems like you're doomed with the two-stage analysis. But more than that, you're actually doomed with that algorithm completely. Like, you can't even hope to analyze these two stages together in some more clever way. In fact, there are situations where that algorithm indeed loses this double log. So this really means that a new algorithm is needed. And our new algorithm circumvents these barriers. In some sense, it still maintains something that looks like an LP solution X, except it's a coarse solution in that it's neither really feasible nor truly monotone, which might sound mysterious, but we'll kind of see what this means. And yet you can still round with respect to this coarse solution over time. Any questions?
Your rounding needs to be monotone. You're saying the solution may not be.
That's right. Yeah. So we're still kind of outputting a legal solution to this online set cover where you can only buy sets and not get rid of them. Right. Yeah. Hopefully this will be less mysterious when you see the algorithm. Well, so good. So if in the adversarial result, you can improve this analysis to exactly like m can be like, so you can get log column sparsity times log row sparsity, which is one of those is in the sort of matrix of constraints. One of those is what you're saying. I have to think of which one. And people have gotten pretty like fine. I think Anupam has the result that nailed it to the log sparsity. So in random order, you have to improve both at the same time, because so if you get m and n together, then log of m times whatever max set size, that's the other sparsity, that's up to a constant the same as mn. So and actually, like, So you'd have to improve both at the same time, and I don't know how to do that. Yeah. Okay, let's jump into the algorithm. So here's our algorithm. As I said, it's called learn recover. And just to recall, this is the exponential time version, and it's for the unit cost setting. So every set costs 1. To describe this algorithm, we're going to imagine in our heads that there's these two objects, this cursive U and this cursive P. Okay, U is the universe of elements that we need to cover. And P, I'm going to call the portfolio. Okay, and the portfolio is initialized to every possible K tuple of sets. So cursive S was the set of all sets we can pick, collection of all sets. And K is a guess for opt. Let's think of K as the size of opt. Using standard online algorithms tricks, you can assume that you just know this value ahead of time. Okay. All right, so I'm thinking of P as like a brute force enumeration of everything that could be the optimal solution. Okay. Here's the algorithm, fairly short. At time T, an element V arrives. If it's already covered on arrival, do nothing, right? No need to, it's already covered. Otherwise, we'll do two things. We'll pick a T uniformly at random from P. Okay, the type of P, recall it's the collection of all K tuples. And so T is a K tuple if we sample it from this thing. And so we can also sample a set uniformly from that K tuple. So what we'll do is we'll buy a random R from this K tuple. And the second thing we'll do is we'll prune our portfolio. Okay, any tuple that doesn't cover the incoming element, we know is not the optimal solution because the optimal solution is feasible. So let's get rid of it. Okay, now you might complain, all we've done, an element shows up, we bought this random set from a random K tuple from this weird collection we have, and then we've kind of pruned the K tuple. Why should we have covered the incoming element? And indeed, we might not have, so let's just do a backup step. Just buy an arbitrary set to cover the incoming element. That's the entire algorithm. Questions about the algorithm? Yes. Yeah, it's weird. Just for cleanliness of analysis. It's probably better to prune before, but yeah. Yeah. But indeed, so then you can kind of decouple, you can kind of analyze progress you make from the sampling and progress you make from the pruning separately. They're not entangled.
So in step 1, you're not considering V.
Exactly. It's completely, yeah.
But you're gonna then, if you don't hit V, the second step, wait, are you gonna throw it out and try again or something?
No, so you just do these two things completely obliviously. So first step, you're absolutely right. You ignore V, just sample from your current portfolio. And now update the portfolio. So basically but you're right, you update it after you do the sampling. And you might have done a bad job sampling, that's okay. We're just doing these two things obliviously. And just to make sure that we're feasible, this backup step is to buy an arbitrary set to cover V, just to make sure we're covered. Yeah. Yeah, I just meant you're right, it's not, yeah. I just wanted you to realize that these are the same types of objects, but yeah, you're right. So maybe Danny, if you see the analysis, tell me if it's not clear after I show you. But I think your intuition is right. That it's a little weird. You're just doing this oblivious sampling, updating this thing. Why should this work? We'll see in a second. Good. So P is this portfolio. I'm thinking of enumerating all possible solutions that are currently in the running. And then from all these solutions, I sample a random K tuple, which could be an optimal solution. And from that optimal solution, I sample a single set. So T is a candidate solution that could be the optimal solution.
So then I'm confused. Why are the two things not the same?
Well, I mean, you're not pruning the T that you sampled. It's the same type of object, but it's not the
Oh,
same.
in step 2. Okay.
Yeah.
In
Right.
Step 1,
Oh, step 1, it is the same. Absolutely. Yes. Sorry.
Also, even if you sample it that contains P, you might still sample an R that does not.
Absolutely. Yeah. And
There is a possibility that at T we buy 2 sets.
so exactly. So good, great. So let me try to answer this. So this algorithm, in rounds where V arrives and is covered, you pay 0. right? In rounds where V arrives and is uncovered, you pay 2, or either 1 or 2, but let's say 2. Yeah, so 1 to buy this R that we sampled, and then to buy the backup set. But let's just be pessimistic and say you pay 2 every time. Great, so to analyze this algorithm, up to a factor of 2, I just need to count the number of times I hit the else clause. And that's what we'll do. Yeah, is that a question or no?
I just asked if in step 1, choose P from P particular.
No, that's, sorry, the tilde notation means uniformly at random.
So I guess I'm very confused. I mean, I don't understand why the process in one is not simply selecting a random set.
Well, so
You're just selecting-
we're updating P over time. So the whole point is,
Oh, so P is not, okay.
yeah.
So first we initialize PBL.
Yes,
Okay,
yes, exactly.
Sorry.
No, that's okay, yeah, no, that's fine.
Now-
It should be clear once we see the right side of the slide, yeah,
But the first one has nothing to do with the.
exactly, nothing to do with V.
Well, it does, because if it was covered, we don't even know.
Sure, that's true,
But other
yes,
than
and
that-
that's crucial, yes. Exactly,
The exponential time comes from the fact that we have.
exactly right. Okay, so the analysis is going to fit on the slide. So 2 cases. Case 1, half of the T in my portfolio cover at least half of U. I should think of this as like most of my portfolio is decent. Okay, at least half of the candidate solutions in my current portfolio cover half of what I need to cover. In case 2, that's not true. So at least half of the T in my portfolio cover less than half. Okay, we agree this is an exhaustive case analysis. That's good. Okay, so let's do case 1. So in case 1, I claim that the R that we sampled covers at least size of U over 4K in expectation. Why is this? Well, half of the T and P cover at least half of U. So the T that I sampled should cover at least a quarter of U in expectation. And now T is a K tuple, recall. There's K sets in it. So if I pick one of the sets uniformly at random, I'll cover like 1 over K of that. Okay, great. So that means that the R that I pick shrinks U. If I imagine deleting from U anything that R covered, U will shrink by something like 1 minus 1 over 4K in expectation. Right? Questions? Okay, great. Case 2, at least half of T cover less than half of U. So I should think of this as most of my portfolio is not very good. Well, if I hit the else clause, what I'm doing is I'm sampling uniformly from the elements that I have not yet covered, right? And if half of the T cover less than half of U, then I should miss basically half of the T's with probability at least 1/2, which means I'll prune them. So I should prune like a quarter of the T's in my portfolio, which means my portfolio will shrink by 3/4 multiplicatively in expectation. And so this is maybe the intuition, like, I don't know if this answers your question, Danny, but yes, you're doing these 2 steps obliviously, but they're kind of chosen so that you either make progress shrinking U or make progress shrinking P.
Why did you shrink? Why did you shrink? Isn't that set at the beginning and fixed forever?
Okay, I didn't write it, but we're imagining that when we buy a set R, we delete from U anything that it covered.
Okay, so
Yeah.
in your case analysis on the right-hand side, you don't mean covers half of all N.
No, I mean the remaining U, exactly. So the picture you should have in your head is like, when you sample a set R, you take a bite out of U. And when you prune the portfolio, you take a bite out of P. Okay? And now you don't know which case you're in actually, because you don't know U, it's unknown to you. And yet, as you're marching along, we agreed it's an exhaustive case analysis, you either kind of bite out of here or bite out of here. Good? Okay, so let's wrap it up. So we said in case 1, U shrinks by 1 minus 1 over 4K. In case 2, P shrinks by 3/4. And I've called these steps suggestively a cover and a learn step. Why? Because we're making progress either covering or learning something about the optimal solution. Right? We're narrowing down our candidates for what opt to be. So U is initially, the size of U is initially N. That's the number of elements we need to cover. How many times can N shrink by 1 minus 1 over 4K before it goes below 1? Something like K log N. What's the size of P initially? It's like M to the K. And we're shrinking it by a constant every time. So how many times can that shrink before it's less than 1? Also, K log M. So if you do the sum of these, if you do k log n plus k log m steps, you have to do at least k log n of the first or k log m of the second, and you'll be done. Right? So if you're done, if you cover all the elements, you're done. If you narrow down the optimal solution, you're also done. After k log mn steps, you're definitely done. Did this make sense? This is the entire algorithm.
So the algorithm will never grow the portfolio.
You
only
never
shrink
grow
it.
it. Yes, exactly.
So in some sense, at the very end, you might just be using the backup step all the time because you killed.
Yeah, that is true. Yes.
So now we cannot use the random order, right?
We're very crucially using the random order, actually. So the reason you can say that the portfolio shrinks here in this step 2, like why is t pruned with probability? Why are half of the t pruned with probability less than 1/2? It's because I know, well, most of them cover less than 1/2 of where I'm sampling from uniformly, right? The random order is ensuring I'm sampling uniformly from this uncovered portion of the space. And the reason I can say that I'm going to sort of miss most of them is because of the random order. Yeah. I mean, this analysis is like false. We know there's lower bounds in adversarial order, so that's like reassuring that. Okay. Any questions? Okay. So we have like 20 minutes left. I can end even sooner, I think. The question that remains to answer is, how do you make this poly time? Okay, we're crucially, as Pedro said, enumerating all possible candidate solutions. This is very expensive, and we're maintaining this thing over time. It's like, you know, space is exponential, time is exponential. And is there any way to reuse the intuition that you're learning or covering? So yes, the answer is yes. Basically, the idea is to, instead of, you know, why are we enumerating all possible solutions is because we're using this to generate a distribution over sets, right? We're sampling R from some like slightly weird distribution that you got from enumerating. And one idea is, can you just directly maintain a distribution over sets and then make progress like learning or covering with this distribution? Okay, so that's exactly what we do. So here's the learn or cover algorithm in poly time, again with unit costs. Let's just initialize the distribution over sets. It's this vector x. Initially, you know nothing, so to reflect our ignorance, again, we'll initialize the distribution to 1/m, just the uniform distribution over all sets. Very, very similar algorithm. When an element v arrives at time t, if it's covered, do nothing. Otherwise, go ahead and just sample from this distribution. And then let's update the distribution. Okay, so for every set containing the incoming element, we just got some signal that that set was like pretty decent. So maybe we'll give it a little boost, a little nudge. We'll just multiply its probability by E. You can choose any constant. E is convenient for the analysis. And then to make sure it's still a distribution, we'll renormalize. So when I said previously that X is like a coarse solution that's neither feasible nor truly monotone, like this is the X I'm talking about. We're not really ensuring feasibility to the LP, even though it like has the same, you know, type as a solution to the LP. Nor is it really monotone, right? Because we're boosting some coordinates and then scaling them back down.
So E here is like the number.
The number E, sorry, yeah. Yes. And then we'll do the backup step again that we did before. Questions about this algorithm? Yes. Great. So so I color coded these, but yeah, of course I remember the color coding. But I expect you to know. I'm just kidding. The step 2 is basically the same as the prune step. So pruning was like, what was the goal of the pruning? It was like learning something about the optimal solution, right? You're narrowing down your portfolio. So here we don't have a portfolio, but we're still going to kind of update the distribution. And what we'll show is that we can make progress kind of learning about the distribution. Well, in some sense, we'll get closer to the optimal solution with this like step 2. That's the analog of the prune step.
Can you show us how this is different from the lines? Like online?
Yeah, great.
They're also scaling steps too.
The main difference is the renormalization step.
Oh, okay.
So they, you know, their requirement was that the solution only ever increase. And we're crucially kind of giving a nudge. So there's 2 differences. One is that when they do a similar multiplicative increase, but they do this until feasibility. We're only giving one small nudge and then not making sure it's feasible, and then renormalizing also. Yeah. So I have a picture later to just kind of highlight this difference. Yeah, that's a great question.
It's a little bit like the the reweighting algorithm for experts.
Yeah, it's very similar.
Except you're increasing, in that algorithm, you punish the ones who are wrong. In this one, you're saying you increase the one that's correct.
Absolutely.
It's kind of similar. I mean, I guess it's the same because then you renormalize.
Yeah. I would love to understand, so it's very similar to the experts. This is how we were inspired to come, we wrote an algorithm and then we figured out how to analyze it. And there is a proof of the experts, like regret that kind of looks like the one I'm getting, like that we do, but not really. And somehow like random order doesn't play a role in the experts algorithm, and it's crucial here. And this is something that, kind of a question I'd love to understand is like how far the analogy goes. I confess I don't really understand. But you're right that it's very similar feeling. And for a while we were trying to just match this analysis to fit it into like a black box experts bound, and we don't know how to do that.
I guess one of the differences is that here you have to apply 100% cover.
Right.
The experts might be wrong sometimes.
Yeah.
Like they regret it. By the end of the you're always more wrong. But here you can't do wrong. You always have to cover.
Exactly. The kind of combinatorial kind of constraint element makes this hard to really mesh with the expert setting. Yeah. Okay, questions before I tell you about the analysis? Yeah.
You know M beforehand, right?
You do. Yes, exactly. Interestingly, you don't need to know n. Yeah, but you do know you have these empty sets. Yeah. Okay, so the idea is to kind of try to mimic the case analysis that we did before, but with a potential function that kind of smooths it out. So it's no longer going to be a case analysis. We'll just write this potential, and then we'll use typical potential function type arguments. So the potential, which I'm calling phi at time t, is the following. It's some weighted sum of two terms, a red term and a blue term. The red term is the KL divergence between x star and xt. X star is the optimal solution. Okay, really to make the scaling work, it's a scaled down version of the optimal solution to make it sort of a distribution, just so it's the same scale as xt. And xt is like the thing that we're maintaining. Okay, plus the second term of the potential is log of the size of ut. So in some sense, so what is the KL divergence? It's some measure of something like distance between probability distributions. And so it's capturing how far we are from the optimal solution in some sense. And then the blue term, log of the size of ut, is measuring how much progress we've made covering the uncovered portion of the space.
So ut is not n minus 1.
The size of ut, it's like if we like when we buy a random set R, we're imagining that we're like deleting from U anything we've covered. So ut is just the uncovered elements. It's like the stuff that we have yet to cover. Does that answer your question?
No, so,
T is a number, so yeah.
Say until 90 we have seen the elements
Oh, good.
which we want to cover. So
Right.
what is more to
So you might accidentally
cover more?
cover stuff in the future. In fact, that's the whole power of the algorithm, is that as you're sampling, you're secretly making progress in the future, even though you don't know. If you were only ever covering stuff you've seen, then there was no algorithm, right? Yeah.
Can you show how this distribution is like X star and XT? I thought XT was going to be the distribution of steps, but X star is going to be the distribution of
It also is, yeah.
Okay.
No, that's fine. Yeah. No, good question. Yeah. I'm for the, I only have so much time, so I'm trying to fit a lot of notation, but yeah, that's exactly right. So imagine the X star is like the optimal sets, the sets in the optimal solution, divided by like, size of ops, or making it a distribution, uniform distribution on the op sets. All right, so in case you don't remember what KL divergence is, it's this term. It doesn't really matter. I don't know if we'll have time to do the analysis. It's the sum over sets of x star s log x star s over x st. All right, so here's the structure of the proof. And this is how potential function proofs often go. We'll bound the initial potential. So this initial potential, it's measuring some kind of like progress, like amount left to go. And it's initially loaded up with like log mn worth of value. And we show that the potential can never go below 0. That's step one. And then the interesting part of the proof is to say that this potential goes down in every step. Well, actually, it might not go down. So in steps where V arrives covered, it's a no up, so nothing changes. But condition on like V arriving and being uncovered, stuff happens. And once you condition on this, we can say that the potential decreases by 1/k in expectation, where recall that k is the size of opt. And so already this should kind of imply the claim, right? So my initial potential is loaded up with log mn. It starts here. It can never go below 0. And it goes down in bites of 1/k. So how many times can it go down before it hits 0? Like k log mn. Right? And we just wanted to count the number of times that it hit the else clause. And so k log mn is exactly what we're shooting for.
In both these claims, you haven't really used random order. Random order seems to come in only to show that claim 2 would be hit like one fraction of the time.
So actually, to prove claim 2, you need random order. And actually, I wrote this exactly here. So the way that you show claim 2 is you can bound the decrease in both parts of the potential separately. Okay, so in every round in which V arrives uncovered, conditioning on this happening, what you can do is you can bound the decrease in the blue part over the randomness of the algorithm. That's the sampling of R. And then you can bound the decrease in the red part over the randomness of the arriving element V, which crucially uses random order. And so fortunately for us, you can kind of cleanly disentangle these two steps. Isaac, this is sort of what you're asking about before. Like this is why we do these two steps separately from each other, just so we can cleanly do this analysis. Right. Any questions? Yeah.
Yeah, I think maybe I'm not quite understanding how the scale divergence works, but it seems like, imagine I had several different solutions that were all equally good.
Yeah.
But they were all, completely different from each other. I can't have that high scale divergence my scale divergence can be great with respect to all of them, which makes it seem like this potential to never get that close to 0, even if I have an optimal solution, because I might have the wrong optimal solution.
I see. In some sense, that just necessarily means you make progress covering then. Like the scale divergence might not go down. So actually, contrary to the other analysis, we can no longer say case 1, we definitely make progress learning and definitely make progress covering. What we can say is in this sort of potential sense, the sum of these two measures of progress is negative. And so they trade each other off. Scale divergence might not go down. In fact, there are situations where it goes up, which is weird. But if it's going up, you're definitely making progress covering.
Okay, because that's in the world where all the sets left are really great. So we don't really
Exactly. You just don't even care. Yeah.
Are those constants?
Actually very reasonable.
In order to prove claim 2, you have to have specific constants, right?
Great, here they are. So can you see this or is this blocking? Sorry. So basically that claim 2 I've split into the two parts. The bound on the decrease in the scale divergence and the bound on the decrease in the blue part, the log UT. Not super important. I have the proof on the next slide just to kind of flash it at you and show you that it's short and manageable, but I don't think we'll step through it. The point is the decrease in the red part, or the change in the red part, is a positive term minus something. And the blue part is minus something which looks a lot like the positive part in the red part. And so what you can do is set the constants. So the red constant is 1, the blue constant is e minus 1, in such a way that these two things just fit into each other cleanly like puzzle pieces. Right? The blue part perfectly cancels out the positive part of the red term, and we just get the negative part of the red part. Okay. And just right. So in this gives the bound that I claimed. Since the initial potential is something like log mn, decreases by 1/k in every round, you get k log mn in total. Okay, so I'm going to skip this proof. I was too ambitious, but it's very short. It's algebra, and there's only so much I can explain with algebra. Given tuition for the algebra. Let me move this again. But basically, it fits on these two slides. Yeah, and it's a short, elegant proof, and actually very similar to the analysis of experts, like the expert regret bounds. They use the same approximations, like log 1 plus z is less than z. These things appear in the same way, basically. Okay, that's basically all I wanted to say. I don't have time to tell you about the non-unit cost setting. The main issue if your sets now cost different things is that you can't just count the number of times you land in the else clause. There's some rounds in which the element arrives. The cheapest set covering that element might be really expensive. Like you need to kind of be more careful. And so, okay, this was actually like a big part of the paper. Like historically, this is where we spent most of our time figuring this part out. But yeah. I can say something quickly. It might not mean anything to you, but the trick is to kind of carefully tune both the rate at which you sample and the rate at which you update the distribution to reflect kappa v, which is like the cost of the cheapest set covering the incoming element. And then you can kind of carefully do the analysis and get it to work out. But I don't have time to talk about this. There's takeaway here is just there's more ideas that go into this weighted setting. Okay. Some philosophy. So you asked this question of like what can we compare this with the Alon et al. Algorithm? And so here's kind of one perspective on this algorithm is that so here's the Alon et al. Algorithm. One way to think about that algorithm is that we're living in some polytope and then we learn a new constraint. And what they do, in fact, this paper by Buchbinder, Anupam, Marco Molinaro, and Steffi Noer shows that you can interpret that algorithm as a projection in KL divergence onto the new polytope, which is like given by the old one plus this new constraint that arrived. You can think of the Alon et al. Algorithm as as like a projection in whatever this means, projection in KL divergence onto this like new polytope. And then there's sampling, right? So they sort of maintain the solution gotten by like repeatedly projecting onto the polytopes that you get every time, and then doing the sampling at the end. And our algorithm is kind of different. So one is we always renormalize to keep it on this, so to keep it a distribution. And we're just giving it like a small nudge towards feasibility. We're not quite going there. We're just kind of increasing the coordinates a little bit. It turns out it is kind of a partial projection in KL, but this is not important. And then we project back down to the sort of simplex. Okay, and we're just kind of sampling as we go along the way. Okay, I won't bother talking about this other thing, but there's some connection of our algorithm to stochastic gradient descent, which is also interesting, but I won't explain that. Okay, so just to conclude, basically, here's the theorem, the main theorem of this paper. As I hopefully explained, we give an order log mn competitive algorithm for pure covering IPs in random order. This is the main theorem of our paper. We show a couple more things which I haven't talked about. We show a lower bound for a batch version of the problem. So if I imagine that the elements are arriving like in batches, in the model I gave you, every element shows up and you immediately have to cover it. You can imagine that elements are grouped in batches by an adversary, and then the batches arrive in random order. So this problem, you might wonder, is this easier or harder than random order? Sometimes you're getting more information, right? You learn like elements in batches, and yet this problem is harder. Good. So for this lower bound, I think you need like a poly size, like square root, whatever, like into the constant size batches. Yeah. So this like batch lower bound implies lower bounds for like generalizations of set cover. In particular, like one of my favorite problems is called submodular cover, which is like in the hierarchy of covering problems, like much harder than set cover, and there you need to lose a double log. I haven't defined what this f parameter is, but it doesn't matter. And it's a nice kind of open question if you can match this lower bound that we give. The best known bound is from a paper of mine with Hanapam a couple years ago for the adversarial order setting, where we kind of lose one of the log factors is a little bit bigger. So it's an interesting question if you can do better in random order. I don't know if I should, I'll just skip this as well. Basically, there's another extension of the random order model that kind of we showed recently, which is like, from solving online set cover. But I imagine I get to sample half of the instance before I even start the game. Can I do any better? Like the second half is going to be shown to me in adversarial order, but I get to sample a random half before I start playing the game. And it turns out that in fact, if you have this like sample access to this thing ahead of time, then you can match kind of the random order bounds. And this is kind of new. Basically, like it's a modified analysis, but uses the same potential that I talked about. Okay, future work. I really want to know if this learn recover idea lends itself to other problems. It's simple enough that I think it has a chance of being something fundamental. Can one do hard recovering problems? In particular, like the kind of burning open question we want to understand is, can you handle covering IPs with box constraints? Okay, like upper bounds on the variables. Our proof like breaks for technical reasons for that setting. Can you go beyond covering problems? Like, can you handle like problems in network design if you assume like online network design if you assume the input comes in random order? I'd love to know more. And finally, is there some like unified theory of like random order algorithms? Can you reinterpret old random order results as learn recover? That's basically all I had. I'm right on time. So thank you for listening and open the floor to questions. Yeah.
So you had unlimited time.
Yes.
Could we do any better than this? Or is this the best one even with unlimited time?
Okay, great. So log n is a lower bound in information theoretically in random order. We can show a log m over log m lower bound information theoretically.
Okay, so it's very close.
It's really close. Yeah. Okay, so yeah. I said we can show that's really adapted from a known bound. So I won't take credit for the log m over log m, but yeah.
So the new algorithm that you have, would that recover the log n times log n bound of Nonunit in the adversarial order?
I think we thought about this. I think it does much worse. I think it's bad in adversarial order.
So here's a confirm.
Yes.
Is your analysis bad, or you think the algorithm?
No, I think the algorithm is truly bad. I need to recall, I don't remember exactly, but I believe the algorithm is truly bad. But you can always do this thing for this particular problem. You can run two algorithms in parallel and always keep track of the best one for a factor of 2. So you can do the best of both worlds if you want.
No, I guess my question was more about whether maybe you just have the right algorithm even for the adversarial setting.
Yeah.
Because sometimes there are multiple algorithms that work, and one of them somehow is the right one.
Right.
That was the.
I don't want to commit, but I think that it's bad. I think I recall us working this out. Yeah.
So the other question, do you need to know the size of the opt into run your algorithm?
You do, but you can learn it. You can guess it basically. So we do this thing guess or double. So you get what you do is you guess opt. You start opt equals 1, and then when I exceed opt by 2, I double my guess for opt and start the algorithm again. And now I incur a cost, which is a geometric series, and so the last term dominates. Constant. Yeah, exactly.
So you presented 2 versions of the algorithm, right? One was the exponential one was the efficient one.
Right.
Are those exactly the same algorithm? I mean, just in terms of the statistical performance, is it
Right.
an identical distribution of, but
Yeah.
expressed differently, or they're?
I don't think they are.
Okay.
That's an interesting question. I don't think so, just because the first step is different, right? So the first step, I'm definitely not sampling uniformly from.
Okay. The
Am I?
potential proof, that's just used for the efficient version.
That's right.
That doesn't apply to the simpler proof for the other one.
Yeah, not that I know of. I think they're different. Let me, not promise that, but I think they're different. Yeah.
Not entirely a serious question, but is this how you came up with it? Did you come up with the exponential?
Yes, I presented it basically in historical order. So the history of this thing is we figured out the exponential time thing. And then we were like, okay, let's make this poly time. We really just need a distribution. What's a natural way to update a distribution? Multiplicative weights increase seems reasonable. How do you measure progress to converging to opt? Anyway, actually initially, I think something we tried is just measuring the entropy of the distribution, and that was hard to analyze. So really like KL to opt was the much better thing to analyze. And then the weighted setting took like many months. So realizing what knobs we were able to turn and what we were even like trying to tune was kind of a lot of the work. And it's too bad I can't. I don't think it's going to make sense if I try to talk about it. But yeah. Thanks. Yeah, I can mention it if you want. So, and this is something I actually don't really understand, but so let's write this function f, which is a function of the fractional vector. F is the sum over v, which are the elements, of the max of 0 and 1 minus the, the fractional amount by which I've covered v. So I'm thinking of f as the fractional uncoverage remaining. Okay, for every element, how much have I not covered it? In some sense, the goal of this process is to minimize f in the smallest number of steps, right? I want to kind of get this to 0, to have no uncoverage. You can show that the gradient of this f is the number of uncovered elements. So okay, so the x is a vector indexed by sets, and so the gradient with the partial derivative with respect to one coordinate, you can show is the number of uncovered elements in that single set, and this is proportional to the expected value that v lands in that set, given that v is uncovered. Okay, so I'm sure if you stared at this, this would be obvious to you. Maybe this is too fast to understand. But the point is that random order is revealing a stochastic gradient of this function. Like because I'm getting v uniformly at random, condition on v being uncovered, I can basically I have a stochastic gradient. And in fact, we're exactly doing kind of mirror descent with the stochastic gradient. Like that's what exponential weights is. But beyond this kind of very high level connection, I don't really, one thing we were trying to do is use mirror descent bounds to just black box this whole analysis, and I don't know how to do that. And this analogy breaks in the weighted setting. So there it's no longer just the number of steps to minimize f that matters, it's some weighted version of this.
Well, actually, one more.
Yeah.
What's the constant E equal to?
No, I mean, I think you can make the analysis work with a different constant. It's just the proof is really nice if I put e. It's like log e becomes 1. It's just kind of clean. Yeah. Yeah.
I guess the constant is related to the definition of drawback versus.
Yeah, that's true. Right. I think you can trade off the constant and the initial potentials. Yeah. You'll make it bigger if you choose something else. Cool.
Thank you again.
Thanks for listening.